Hello, I'm Suhas Lohit, and I'm very happy to present our paper on model compression using optimal transport at WACP 2022. My co-author is Dr. Michael Jones, and we're both researchers at Mitsubishi Electric Research Labs in Cambridge, Massachusetts, in the United States. Model compression is an important topic in deep learning research, as the most accurate models are usually slow or require large amounts of memory for storage. These disadvantages prevent easy deployment in resource-constrained settings like mobile phones. A common method for model compression is by using knowledge distillation, where the knowledge from a larger, more accurate teacher network is transferred to a smaller network called the student. We use image recognition as a canonical application in this work. So the earliest works in KD by Jeff Hinton and others did this by training the student using a combination of the usual cross-entropy loss using one-hot labels as well as the KL divergence between the student and output and the soft labels obtained from the teacher outputs. Subsequently, the student network accuracies were further improved by providing supervision at the intermediate layers. For example, in FitNets, Euclidean laws can be used to match the teacher and student features for each image. In relational knowledge distillation, the distance matrix computed on student features are matched with the distance matrix computed on the teacher features. As we will show in the next slide, encouraging one-to-one matching between teacher and student features of corresponding images as in FitNets is unnecessary and may be restrictive. At the same time, only matching the distance matrices between student and teacher's features, while the individual features themselves may not be similar at all, like in relational knowledge distillation, may be too loose a constraint. Here we ask, can we find a supervision signal that is something in between? We propose matching the distributions between teacher and student features. Rather than resorting to methods like adversarial matching, we use optimal transport, which is a mathematically principled way to measure distances between two distributions. This slide shows the motivation for optimal transport and how it is a relaxed version of FitNets. In this example, our goal is to train the student to classify between stars and squares, given a trained teacher. Blue shows the teacher features and the orange shows the student features. The left image shows the feature distributions before training the student network, while the right shows the feature distributions after training the student network. The line in the middle, which is in blue, shows the true class boundary. Note that it is not necessary that the teacher feature of, let's say, image 1, which is x1, be close to the student feature of image 1, which is y1. It is only that there are class-wise distributions that need to be close to each other. For example, x1 can be close to y3. A loss function, which is a combination of the cross-entropy loss and the optimal transport loss, allows this solution. It does not require the one-to-one alignment that FitNets needs. As the loss function shows, we can compute the OT distance at multiple layers of the teacher and the student. This slide shows the explicit formula for OT distance at layer L. The OT distance is the optimization problem shown here, where we want the optimal transportation matrix T, also the alignment matrix, given a cost matrix C. We use the cosine distance between the teacher and student features for each batch to compute the C matrix. However, solving this problem is computationally expensive. In order to solve it more efficiently, we experiment with two different relaxations that are in literature. The first is called inexact proximal optimal transport, IPOT, and is solved using the algorithm on the right. And the other is called the relaxed earth movers distance, REMD, which is shown here. Both of them can be easily integrated with modern deep learning toolboxes, which use automatic differentiation. I will now show some experimental results on image recognition datasets. On CIFAR 100, we conduct experiments with several teacher-student combinations and show that the optimal transport loss functions outperform other methods like FitNets, relational KD, RKD, and many others. And by combining with methods like contrastive representation distillation, called CRD, we can get very, very good performance. We also see similar trends in the case of ImageNet and SVHN datasets, where the optimal transport methods outperform other feature matching based methods like FitNets and RKD consistently. This slide shows references to important related methods, and thank you for listening.